Hey there, welcome to The Art of Science, the channel where I help you understand machine learning and computer vision using seemingly random examples. What's the connection between image segmentation, your favorite online shopping website, search engines, and sheepdogs? While this may seem like the beginning of a terrible dad joke, I promise you that all of these things share a common thread in machine learning. Even the sheepdogs problem, you ask? Why, yes, indeed. It turns out that clustering can help solve all of these things. Let's dive into a popular clustering algorithm called k-means clustering and see how it can help our friend, the sheepdog. A big caveat before we begin. Clustering isn't necessarily the best solution to each of these problems, but it simplifies the problem quite a bit. For example, you could cluster similar pixels in an image to achieve image segmentation. You can cluster items in your shopping website to recommend items to a buyer based on what other buyers have bought. You can group together similar search results and topics to speed up your search engine and perhaps make the results more relevant. K-means is really useful, but it does suffer from some limitations, which we will see in a bit. With all that said and done, let's hear the story of Sheepdog and the K-means crystal. Long ago, about a week ago to be exact, there lived a sheep farmer somewhere where sheep live. The farmer had a trusty sheepdog whose sole responsibility was to keep the sheep together at all times. The farmer had just one type of sheep, so this was relatively easy for Sheepdog to keep track of. He didn't care which sheep was Jack and which was Jill, he only cared that they were the same type. One evening, after he had herded in the sheep for the night, Sheepdog went for a walk. Well, all dogs do, I guess. Suddenly, there was a loud crack of thunder, and an elf appeared in front of Sheepdog. "Don't be afraid," said the elf. "I'm here to help you." "Woof," said the sheepdog. Through the power of state-of-the-art NLP, we are now able to hear what the dog says in English. Help me? Yes, help you. Very soon, you will be overwhelmed. When that happens, use this. A glowing light appeared in the elf's hand. He gave it to Sheepdog. It was a purple crystal that had the engraving K on the front and some elvish gibberish on the back. "What do I do to use it?" asked the dog. "Those who know don't ask, and those who ask don't know," replied the elf. Right, I don't know," said the dog. Okay. Just turn it in your paw once when you need help, and it will work. Be careful though. Each time you use the crystal, it loses power and will stop working well eventually, warned the elf. "Sure, thanks, strange elf, I guess," said Sheepdog, and the elf vanished. The next day, the farmer brought in a new kind of sheep and asked Sheepdog to keep them separate from the existing sheep. They should not mix. Make sure of that, Sheepdog. Since the animation budget here at the channel is less than 1 parts per million of major animation studios, we now bring you the action from a bird's eye perspective. We do promise that what you see are indeed sheep and Sheepdog. Now, where were we? Yes. Sheepdog was happily managing one type of sheep when the farmer brought in a new type of sheep to join the flock. Sheepdog tried to stand in between the two types of sheep, but soon found it hard to keep the two types from socializing. You know how it is with sheep. Remembering the crystal, he took it out and turned it once. Instantly, a virtual clone of himself appeared next to the new sheep. Composing himself after that stunning display of magic, Sheepdog asked the first clone, "What are you?" "I'm a centroid," replied the clone. You take care of those sheep that are closest to you, and I'll take care of the ones right here." "Okay," said the clone, and began herding the new sheep away from Sheepdog's flock. The farmer couldn't see the virtual clone because he didn't have the crystal, and so was amazed at Sheepdog's ability to manage the different sheep efficiently. He decided to scale up his business and got another variety of sheep for Sheepdog to manage. Once again, Sheepdog turned the crystal in his hand and a second clone appeared. Together, the three dogs managed to group the similar sheep and made sure that they didn't mix. As time went by, the farmer kept adding new types of sheep and was amazed to see one dog manage them all. However, soon, Sheepdog began to notice that the new clones were appearing in random positions, and oftentimes they were appearing in equidistant positions from two types of sheep. As a result, two or more clones started fighting with each other over which sheep to manage. Since each clone would manage the sheep that was closest to them, they began to manage more than one type of sheep. The crystal had lost its power, and Sheepdog wasn't able to keep the different kinds of sheep properly separated. The end. So let's summarize K-means based on this story. You own the K-means crystal. Each sheepdog is what we call a centroid, and each sheep is a data sample. While you can decide how many centroids you want, you can't specify where they will be initialized. Here are the 4 steps in the K-means algorithm. First, decide how many centroids you want, and they will be randomly initialized around your data samples. Second, map or associate each data sample to the closest centroid. Third, update the position of each centroid to be the mean position of the data samples of that cluster. Fourth, repeat the steps 2 and 3 until the centroids don't move much from their positions. In this case, we've already seen them converge. Clearly, the quality of the clustering results when using K-means depends on the initialization of the centroids and the number of centroids K that are chosen. This usually means that we have to run K-means a bunch of times to get satisfactory clustering. For example, in these 3 cases, you can see that in the first 2 examples, the value of K remains the same, but because the centroids were differently initialized, you can see that the second example produces better clustering results compared to the first. And in the case of the third example below, by reducing the number of clusters K to 3, we are able to get better clustering results. Given these 2 principal limitations of K-means, how can we address these? First, what should K be? And second, how can we better initialize the centroids? To have a better guess for the number of clusters we should use, we can use something called the elbow rule. Before we look at this, we need to understand how K-means clustering is evaluated. K-means clustering uses a metric known as the inertia score to measure how good the clustering is. The inertia score is the sum of squared distances of each point from its respective centroid. Thus, a lower inertia score is usually a good indicator of how well the points have been clustered. In case that was a mouthful, here it is in plain English. Add up the squared distance between a point and its centroid for all points for all centroids. That wasn't so hard, was it? Now, how do we use this with the elbow rule? Basically, we run repeated experiments by increasing the value of K and then plot the inertia score of each run against the corresponding value of K. And then we pick the value of K that is on the elbow of the curve, hence the name. This isn't always perfect, but it's a good rule of thumb. See what I did there? To improve the initialization of the centroids themselves, K-means++ was proposed in 2006. Now, before you get ahead of yourself, this isn't K-means with encapsulation and polymorphism. In K-means++, more care is taken when initializing the centroids. Each new centroid is initialized as far as possible from existing centroids, and this makes it easier to get better clusters. The trade-off here is that you sacrifice more compute to get better results and avoid the need to have repeated runs of K-means. So as you can see here, the 2 clusters are well separated. So that's all there is to understanding k-means. In the next video, I'll walk you through implementing k-means from scratch in Python. Until next time, happy learning.